So in the first part, we're trying to find the spring constant, and we know that F is equal to K times the length, kappa times the length. So kappa would be F divided by the length. The force was, what, 2. The length was 1/2. 2 divided by 1/2 would be 4. Now in the B part, all of these are in the formula that I gave you on the PowerPoint. We know that the omega naught is the square root of kappa divided by m. And we just determined that kappa was a 4. We're given m as a 16. So the square root of 1/4 would come out to be a 1/2. So that's our omega naught. The natural angular frequency. The natural period, that's P naught, we know is a 2 pi divided by omega naught. So that'd be 2 pi divided by 1/2, which comes out to be a 4 pi. The natural frequency is just the reciprocal of that, so that'd be 1 over 4 pi. Now to find our amplitude and phase angle, we're going to need to solve the differential equation and do our appropriate conversions. So let's construct our differential equation. We know that for a spring, our differential equation is going to be mass times the second derivative plus the coefficient of friction times the first derivative plus kappa times y equals 0. And we were told that this was undamped. If it's undamped, we know that lambda is 0. So we have just my double prime plus kappa y equals 0. And we're told that the m was 16, so this comes out to be 16 y double prime. We found kappa up in part A to be 4, and we'll solve that. This gives us a characteristic equation of 16r squared plus 4 equals 0. Our 16r squared equals -4. R squared is -1/4. Doing the square root of both sides, we get plus or minus the square root of -1/4, which comes out to be a 1/2 I, which tells me that my solution is going to look like this. Some constant. Now that's a 0 plus or minus 1/2 I. So this constant would be e to the 0, which is a 1, and then the cosine of 1/2 t, C2 sine 1/2 t. So there's our general form of our solution. Now to find the equations using those conditions, initial conditions, we're going to need the derivative of this, so we'll go ahead and find the derivative. The derivative of cosine 1/2 t would be a negative sine 1/2 t times 1/2, and the derivative of sine 1/2 t would be just cosine 1/2 t times 1/2. Write that all over again. Okay, so let's take the first one here. We know y of 0 equals 2, so if we take our y, this will be a 2 for y, c1 times the cosine of 0, which is 1, plus c2 times the sine of 0, which is just going to be 0. So we get c1 equals 2. And if we use the derivative here, we get y prime, which is 0. Now negative 1/2 sine 0 is going to be 0. 1/2 c2 cosine of 0 is 1, so that's just 1/2 c2. Multiply both sides by 2, and we come up with a c2 is 0. And so our equation here is going to be y equals c1 cosine 1/2 t plus 0. So there is that. Now, to find, well, we don't really need to do anything to this, but because it's already in the right format. The amplitude, to find the amplitude and the phase angle, we need this in the form of y equals a cosine omega t minus, not plus, phi. So that phi is our phase angle that we're looking for. Well, this is already a 2, so a is a 2. Cosine, this is going to be a 1/2 t minus 0, and so our phase angle would be 0. So a would be 2, and phi would be 0. Now I'll go ahead and sketch a graph of that. So here's what the graph would look like for that. The 2 cosine 1/2 t, the normal period for cosine is 2 pi. That 1/2 tells me it's going to be 2 pi divided by 1/2, which comes out to be a 4 pi. And so the cosine function starts out over here at 2 and has a period of 4 pi, so 1, 2, 3, 4 pi, and so it'll be back up here at 2, okay, halfway in between at 2 pi, it'll be at negative 2, and so the graph would look something like this. Not a very good sketch on the computer, but draw it off on your calculator and do better on a piece of paper. Okay, so I won't go through the rest of them because they work pretty much the same as this. You'll just get different values of a and phi, but that's pretty much the way you're going to be doing all the problems in this chapter.